Now back again to the ionic bond. When the electronegativity difference between the atoms involved in the chemical reaction is higher than 1.9, we expect the bond to be ionic. Let's apply that to our example. Sodium electronegativity is equal to 0.9 and chlorine is 3. The difference in the electronegativity is equal to 2.1, which is higher than 1.9. That is why ionic bond forms. During the formation of the ionic bond, the difference in the electronegativity results in the transfer of electrons from the lower electronegative atom, sodium, to the atom with the higher electronegativity, chlorine. Let's look how we can explain the formation of the ionic bond between the sodium and the chlorine using orbital interactions. First, you have sodium electronic configuration Ne3s1. For chlorine, it's Ne3s2 and 3p5. Notice that the 3p5 needs 1 electron to be completely filled with 6 electrons. This electron usually transfers from the 3s1 to the 3p5. For that, you will have the sodium losing the electron in the 3s, and chlorine will gain 1 electron and will have 6 electrons in the p orbital. The second type of bond is a covalent bond. This type can either be non-polar covalent or polar covalent. If the difference in the electronegativity is less than 0.5, it is non-polar covalent bond. And if the difference in the electronegativity is between 0.5 and 1.9, it is polar covalent bond. Let's see first the non-polar covalent bond. This type of bond, like we said before, forms when the electronegativity between the two atoms is between 0 and 0.5. The atoms of this bond share electrons because the difference in the electronegativity between atoms is very small that both atoms can't pull electrons towards themselves, leaving the electrons between the two atoms. One example is a covalent bond between two chlorine atoms to form chlorine gas. Two atoms with a difference in the electronegativity equal to 0 share 2 electrons for each atom to reach the electronic configuration of argon. One covalent bond is formed by the overlap of the two p orbitals. Like we said earlier, the electron configuration of chlorine is Ne3s2, 3p5. This means if two chlorine atoms each one of them share 1 electron, each one of them will have 6 electrons in the p orbital. It might be simple to say that these two orbitals are going to share 1 electrons for each one of them to have 6 electrons, but the fact is that what usually happens is a combine of 2 atomic orbitals to form a new molecular orbital. For example, in this case, for chlorine in the px, the 1 electron in the px orbital usually combines with another px atomic orbital, and the result is the formation of a new molecular orbital. Another example is a covalent bond between 2 oxygen atoms to form oxygen gas. 2 atoms share 4 electrons for each to reach the electronic configuration of neon. 2 covalent bonds are formed by the overlap of the 2 p orbitals. If we looked at the electronic configuration of oxygen, we found that it is 1s2, 2s2, 2p4. This means the p orbital needs 2 electrons to have a complete filled p orbital. This is why 2 orbitals each share 2 electrons for them to be filled with 6 electrons. Here, 2 nitrogen atoms share 3 electron pairs to form 3 covalent bonds in between. Now, if we look at the electronic configuration of nitrogen, we see that it is helium 2s2, 2p3. This means p orbital needs another 3 electrons to be completely filled. This is why 2 nitrogen atoms each share the 3 electrons for them to have 6 electrons each. Now moving to carbon. Carbon has the ability to form a maximum of 4 nonpolar covalent bonds. For example, in methane, the carbon has 4 valence electrons. It shares the 4 electrons with the other 4 hydrogen atoms. By that, the carbon becomes surrounded by 8 electrons. The third type of chemical bond is a special type of covalent bond that occurs when the difference in the electronegativity is between 0.5 and 1.9. The atom higher in the electronegativity pulls the electrons more than the other atom which is lower in the electronegativity. Yet the difference in the electronegativity is not that significant to enable atom with a higher electronegativity to completely pull electrons towards itself. And the result is that electrons are not equally shared between both atoms. The pull of electrons towards one of the atom more than the other creates a partially positive charge, delta positive, on the atom lower in the electronegativity, and a partially negative charge on the atom higher in the electronegativity. Usually we indicate the polarity using a dipole arrow with a head pointing to the more electronegative atom. One famous example of polar compounds is water. Water consists of one oxygen atom and two hydrogen atoms that share one electron pair each. If you looked at the electronegativity of oxygen, it is equal to 3.5 and hydrogen 2.2. The difference in the electronegativity is equal to 1.3, which lies between the 0.5 and 1.9. By that, water molecule contains two polar covalent bonds. You can see that the space-filling model of water shows a higher electron density over the oxygen and low electron density over the two hydrogen atoms. Notice the angle between the three atoms is not linear. The angle is 104.5 degrees. This happens due to the repulsion of bonding pairs with the two non-bonding lone pairs on oxygen that we will discuss in details in the later lectures. Another example is hydrogen chloride. You can see that the polar covalent bond that forms between the hydrogen atom and the chlorine atom makes the hydrogen atom slightly positive. We give it the sign delta positive. Where chlorine acquires a partially negative charge, we give it the sign delta negative. Notice the dipole bond arrow with a head pointing to the more electronegative atom. Let's compare the major differences between the three types of bonds. The probable bond that can form between metals and non-metals is the ionic bond, and the electronegativity is usually greater than 1.9. Between non-metals or non-metals and metalloids, the polar covalent bond can form if the electronegativity is between 0.5 and 1.9, or the non-polar covalent bond if the electronegativity is less than 0.5. Now let's move to this exercise. Using the bond dipole arrow and the symbols delta plus and delta minus indicate the direction of polarity in these covalent bonds. Carbon-oxygen, nitrogen-hydrogen, and carbon-magnesium. In A, you can see that the carbon has electronegativity equal to 2.5 and oxygen equal to 3.5, which makes the oxygen has a higher electronegativity than carbon. So the electrons will be pulled toward the oxygen atom, making the bond slightly polar towards oxygen. The dipole arrow head pointing to oxygen. For nitrogen bond hydrogen, nitrogen has higher electronegativity, so the dipole arrow head points towards nitrogen. Lastly, the dipole arrow in carbon-magnesium bond points towards the carbon because it is more electronegative. Now let's look at another exercise. Classify each bond as non-polar covalent or polar covalent using the symbol delta plus and delta minus. Indicate the direction of polarity in each polar covalent bond. Knowing that the oxygen electronegativity equal to 3.5, hydrogen 2.1, and nitrogen equal to 3. First, to know the type of bond between oxygen and hydrogen, we need to calculate the difference in the electronegativity between the two atoms of oxygen and hydrogen, which is equal to 3.5 minus 2.1 equals 1.4. Notice 1.4 lies between 0.5 and 1.9, so it is a polar covalent bond. The direction of polarity of the dipole arrowhead towards the higher electronegative oxygen. The bond between nitrogen and the hydrogen. The electronegativity difference is equal to 3 minus 2.1 equal to 0.9. So it is a polar covalent bond as well, with a polarity direction towards the nitrogen atom.